just now. But Cosmo Harrigan is going to talk next.
Here we go.
Okay. The floor is yours.
Thank you. My name is Cosmo Harrigan. I'm going to present a brief overview of work that I've found interesting from the past 2 years that, extending on Leslie's comments of the increasing complexity of what is meant by deep learning and how it might be applied to the field of AGI. Here's a brief outline of what I'm going to present. First, I'll describe how we might view AGI in the context of deep learning, and I'll present an alternative definition for deep learning, and then we'll review several fields and work that has been conducted in them. We'll go through some unsupervised learning and intrinsic motivation models, generative models, program learning and memory, learning to act, issues with one-shot learning and data efficiency, transfer learning and attention, and then we'll briefly discuss several additional architectures and potential avenues for the future. Because this is a brief talk, I'll only be able to go over these models in very high-level detail. A lot of the content that I'll be presenting is based on the papers, which I have cited in the footnotes. First of all, why do I think deep learning is relevant for artificial general intelligence? I think it's relevant for 2 reasons. First, because the methods that are encompassed by the term deep learning are continually expanding in scope. They're beginning to include ways to address memory, program learning, unsupervised learning, action learning, attention, and other fields. And secondly, because deep learning is increasingly being used in conjunction with other systems to produce hybrid systems. To begin with, let us consider deep learning in the context of universal intelligence, following up on some of the tutorials from yesterday. It was nicely put in this paper from Vaness in 2011, where he defines planning as Expectimax search into the future, and learning as the use of a Bayesian mixture over Turing machines to predict future observation and rewards. Now this is what's defined in the AXE framework. We can view practical methods for AGI as approximations of this sort of ideal, and we can view deep learning as one such method. I like this alternative definition of deep neural networks that was presented in Schmidhuber's review paper, where he defines the program implemented by the network and several pieces of terminology, such as a partially causal sequence, the topology of the network, the concept of weight sharing, credit assignment paths, and potential causal connections, and uses this to define what we mean by a deep neural network. We'll go through this very briefly. He defines the definition of the network as its program, or i.e. its weights, and the partially causal sequence defined by the network, including the concept of events. The network encodes a topology, and there is a crucial concept of weight sharing in many types of deep neural networks. We also have the concept of credit assignment paths through the network, and potentially causal connections. I apologize, we're going through this rapidly, but there's not a whole lot of time, so we can go through this in more detail offline. Finally, these concepts are put together to define the concept of depth, and in that sense we have a definition of deep learning which is extremely general and can encompass a very rich variety of architectures. Now we'll briefly review the different work that I've found interesting from the past 2 years in this field. We'll begin with intrinsic motivation. Now, intrinsic motivation is a method to allow embodied agents to satisfy an internal drive for discovery, which could be defined in a number of possible ways, rather than to directly aim to solve a higher-level goal function. This is especially useful in environments and settings where you have sparse rewards or long delay before you receive rewards. A recent work was called the Hierarchical Dq Network. This integrates a hierarchical value function at different temporal scales with an intrinsic motivation function to approach deep reinforcement learning in a somewhat more sophisticated manner. They're able to learn intrinsic goals, also called options, as defined by Richard Sutton. and a control policy that composes these options to achieve long-term goals. Here's an illustration of their architecture, where we can see the low-level controller and the meta controller coupled with the environment. And I've included their algorithm. Now here's an interesting application of this. In the original DQ Network paper, Montezuma's revenge was presented as one of the examples that was difficult for the algorithm to achieve good results in. The reason for that is because it is an instance of a very delayed reward where you receive it at the very end of the game after performing a complicated sequence of actions. This hierarchical DQN algorithm, as we can see, achieved very good results in comparison to the original results in red. Moving on to another recent work, they have first of all outlined several possible functions that could be used as intrinsic motivation functions. Of these 5 possibilities, they focus on the last, the concept of empowerment. While there's many ways in which we could formally define internal drives, we will see that they all involve an unsupervised learning method that allows the agent to try and arrive at some measure of value of the information that it's gathering in the long term to achieve its goals. In this paper, they presented a mutual information-based method, which they called empowerment, that allowed them to achieve this type of reasoning. Moving on to another theme that I found interesting recently is that of generative models in deep learning and their applications to AGI. They're often based on variational autoencoders, which are latent variable probabilistic models, and they're used in an unsupervised learning setting. Here's an interesting example where on the left we have examples provided to the system. On the right, it has learned to hallucinate additional classes. It has generated them based on its model in the style of the example on the left. An additional work that was done on top of this is the generative adversarial network. In this framework, they train 2 models. One is a generative model that captures the distribution of the data, and the second is a discriminative model which attempts to determine whether the sample that it is presented with came from the training data or from the generative model. This corresponds to a minimax game. These types of generative models were applied recently to present a learned model of chairs in which they could vary latent features to generate new visual images. We can see here that they were able to vary various features such as translation, color, etc., to generate different chairs that were not presented in the training data. And here is their architecture. There has been additional work in this regard as well, where they have combined Laplacian pyramids with the generative adversarial network model for class image generation. Now I'll move along to the concepts of memory and program learning and several examples of recent work that have been done in that regard. There was a recent extension called the Feedback Recurrent Memory Queue Network, which allows for a context-dependent retrieval of memories for deep reinforcement learning. And in this way, they were able to utilize an attention model to determine which memories they need to focus on for computing the value function. The model is illustrated in part E. Along with memory, we have the concept of program learning, which is a key aspect for AGI. One of the hallmark papers in the past 2 years was the neural Turing machine, which coupled neural networks with external memory resources, which I'm sure many of you have seen. Here we have a diagram of the architecture, and now we will describe some of its properties and applications. They have applied it to copying, sorting, and associative recall in simple tasks. And essentially what they have constructed is an architecture that has extended standard recurrent networks to allow it to utilize a large external addressable memory. Essentially, this is analogous to a working memory system. Additional recent work extending this idea is the neural GPU. This, in contrast with the neural Turing machine, is a highly parallel architecture, which is designed to make it easier to train and more efficient. They applied this to several simple algorithmic tasks, such as long addition and multiplication of numbers in binary. Another interesting work in this vein is the neural programmer interpreter. This was a recurrent and compositional network that learned to represent and execute programs in Python. It's interesting to look here at their results. They compared it to a traditional sequence-to-sequence neural network, illustrated in blue, and the neural programmer interpreter, illustrated in red. First, they look at the sample complexity, and we can see that after about 8 training examples, it achieves perfect accuracy, whereas the sequence-to-sequence network took much longer. In the second figure, we can look at its generalization ability, where you can see that it generalizes much better in the red figure to much longer sequence lengths. Moving to the next topic of neuroevolution and learning to act. Neural networks can not only be used for feature learning, but also as a policy search method in reinforcement learning. We can do this by representing the controller as a neural network and optimizing it using genetic algorithms. For instance, this was done in these sequence of 3 papers for learning to drive from screen pixels in the Twerks simulator. In this case, they utilized a genetic algorithm to train the convolutional network and the recurrent neural network. Note that they did not use backpropagation in this case. In another recent work that I'm sure you've all seen, they used backpropagation rather than neuroevolution to train this end-to-end network for taking actions in Atari games. These are both examples of the field sometimes known as deep reinforcement learning. The next field that I'd like to briefly summarize that I think there's been interesting work on is that of data efficiency, or one-shot learning, which has been mentioned in the previous presentation. There's a couple good illustrations here. If we look at part 1, we see that we're given one example highlighted in red, and the problem is to look at the additional remaining examples and determine which ones belong to the same class. Now, humans can do this easily given one example, and the problem is to construct systems that can also have that ability. If we look at the second example here, the problem is to be given one example and to be able to generate new examples. This is known as one-shot learning. Many traditional recent methods, such as original deep reinforcement learning methods, are highly data inefficient, which is certainly a drawback. But there have been several recent attempts to overcome this issue. This is one of them, called episodic control. What this does is it reenacts observed successful policies using a memory by following highly rewarding sequences of experiences that have achieved good results in the past. We can view this as an instance of a fast learning system, a system that is based on non-parametric memorization of certain experiences. The context in which this is presented is, as I mentioned, that humans and animals are able to learn very rapidly from single examples, utilizing multiple methods of memory and decision systems based on the setting in which they find themselves. For example, sometimes it is appropriate to use model-based planning that takes more resources, but sometimes you need to make fast decisions in which you need less resource-intensive methods. In this work, model-free episodic control, they presented a quick-to-learn instance-based method that is utilized as a rough approximation when less resources are available. Other work in this vein of data efficiency and one-shot learning was presented in this paper called One-Shot Learning with Memory-Augmented Neural Networks. In this case, they were able to rapidly learn from new data and utilize it for further instances. This is more in the deep reinforcement learning setting, where the concept of experience replay stores prior experiences and replays them internally in order to continue training the model. However, traditional experience replay does not have a method of prioritizing memories to effectively train the model in an efficient manner. In this work, however, from Schall in 2015, they introduced prioritized experience replay, where they have a method of sampling based on predicted importance of the memories. Another interesting work was called actor-mimic multitask learning. In this case, they were able to train a single policy network using the guidance of several expert teachers how to act in a set of distinct tasks. And finally, there's another example called deep skill networks, where they were able to introduce an architecture called the Hierarchical Deep Reinforcement Learning Network for skill reuse for lifelong learning. This is an illustration of their architecture. Finally, in this section was introduced the universal value function approximator. What this does is it extends the concept of a value function from reinforcement learning. Rather than simply applying to the value of a state, it generalizes it to the value of a state-goal pair so that it can be generalized to new goals as the agent is encountering new experiences and requirements. Finally, I'll present briefly several additional architectures that have been presented recently: the deep recurrent Q network, highway networks, ladder networks for unsupervised learning, the dueling network for learning an advantage function in conjunction with the value function for learning from screen pixels. There have even been applications to automated theorem proving, and a proposal for an architecture that combines a recurrent neural network controller with a recurrent neural network model that utilize each other to learn to predict and control in an environment. Moving to the end of the talk here, I'd like to point out that many of these models take inspirations from neuroscience. It was presented nicely in this recent paper, where they said that we are finding that structured architectures are used, including dedicated systems for attention, recursion, and various forms of short and long-term memory storage. And furthermore, these architectures are increasingly heterogeneous, enabled by a sequence of, or a series of interacting cost functions, aiming to make learning data efficient and precisely targeted to the needs of the organism. In conclusion, I believe we will see more hybrid models, and we may see work aiming to address planning and reasoning and building cognitive architectures using components from deep learning. By doing this, future generations of neural networks will likely look very different from the current state of the art, endowed with intuitive physics, theory of mind, and causal reasoning. And we may see that more structure and inductive biases could be built into the networks or learned from previous experience with related tasks, leading to more human-like patterns of learning and development. So thank you. In conclusion, I think that by expanding the scope of deep learning and combining them in hybrid systems, they are at least a very relevant topic for the study of artificial general intelligence. Thank you.
Thank you very much indeed for that very, really deep review